In this video, we will learn about how to use our theories of bonding, so valence bond theory and molecular orbital theory, to explain some observations that have been made, which is that pi bonds tend to kind of interact with each other and undergo extended delocalization beyond just two atoms at a time. So it turns out that valence bond theory does work very well for sigma bonds and isolated pi bonds, but it doesn't do a good job of explaining when an electron is delocalized beyond two atoms. So for an example of this, if we look at this anion right here, it looks like we have just a carbon atom that is negatively charged and a double bond nearby. But if you go through and look at this molecule experimentally, what you find is that you have the three carbon atoms like so, where the bond distance between the two left carbons and the two right carbons are exactly the same. And furthermore, you can see that the charge is not isolated on this right carbon atom, but rather is shared between kind of the left side and the right side equally. So that's kind of weird, right? That negative charge is not isolated on one atom, it is delocalized to other places in the molecule. Another observation that has been made is that if you compare just an isolated pi bond to pi bonds that are kind of bonded together like this, where it's kind of a double bond, double bond arrangement, what we see is that the double bonds on the right are actually different from the double bonds on the left. So something about putting them in a row like this or in conjugation with each other causes them to behave a little bit differently. So we have two models for explaining this, delocalization. And so the first one is to use valence bond theory and just add a piece to it. And the piece that we're adding is resonance. So what that looks like is something like this, where I am showing a Lewis structure on the left here, where the negative charge is on one of the atoms, and then I show another Lewis structure on the right here, where the negative charge is on another atom. And I kind of view these and take an average and get to a similar picture to what it was given up here. Another approach is to use molecular orbital theory and a version of that called Huckel theory. And Huckel theory is basically doing MO theory with just p orbitals. And what you end up getting looks something like this, where you, since you're only thinking about p orbitals, you end up only thinking about pi molecular orbitals, like so. And so these would be the pi molecular orbitals for this molecule on the left here. So let's look at these different ideas. Resonance first. So resonance is this idea that there are a lot of different resonance forms that you can draw for a molecule. In other words, you can draw a lot of different valid Lewis structures for a molecule. With resonance, what we're thinking is that some of these resonance forms are more significant than others. So we take a weighted average of all of the possible resonance forms, and by doing that, we arrive at a resonance hybrid that is a good model for the actual molecule. Right? And so again, that resonance hybrid is this weighted average. I think it's important to kind of go over what the way you might have learned this in the past was. And so the Lewis structure approach to resonance is to kind of take a group of atoms that have been sigma bonded together and then add in pi bonds until you can do it differently. Right? So what I mean is many people learn it like this. So let's look at an example for NO3 anion. So what you might do is to start by drawing the atoms out like this, putting in as many electrons as you can with single bonds and lone pairs, and then you might go through and say, well, I could put a double bond here, which would then leave the other electrons to be out here, charges like so. Then you could look at the structure in the middle here, put the double bond here, lone pairs out the other two oxygens, negative charge, like this. And then finally on the right structure, you might say, well, then I can do it like that. Same idea with charges, right? And so that's how you might generate your three resonance forms. The organic chemistry approach to this resonance problem is a little bit different. And so the idea is actually to start with a given Lewis structure and then find your way toward the other resonance forms by using curly arrows. And so let me show you what that looks like for the nitrate anion again. So rather than kind of drawing out three nitrates and dropping in electrons until things all make sense, what organic chemists do is start with a known Lewis structure that makes sense, and then look for relationships between resonance forms. And so it might look like this. So I might draw an arrow that looks like this, and like so. And so the idea of these red curly arrows is to help me think about what the next resonance form might look like. So I'll draw my double-headed resonance arrow there, and then get to a structure like this. And so what I'm trying to see here is that it looks like I take this lone pair, so my arrow always starts at a lone pair, or a pair of electrons. It then turns into essentially a double bond between oxygen and nitrogen. So that is this extra bond right there. And then one of the bonds here, essentially the pi bond between nitrogen and oxygen on the top here, now has become a lone pair on oxygen. So that would be, let's say, those two right there. Fill in some charges for you. And so the point of doing it this way is that it's a little bit easier because you're starting with a given structure. You don't have to reinvent the wheel 3 times like you did up here. And this shows you kind of the relationship between resonance forms. Right? And so you should be able to draw another resonance process that gets you to the third resonance form of NO3-. So a really important thing to understand when it comes to resonance forms is that these arrows are not signifying electron movement at all. Right? The electrons are not moving when it comes to resonance forms. The purpose of these arrows is just to show the relationship between these two structures. There's no electrons kind of changing locations in the molecule. So this idea may seem a little different at first if you didn't learn it this way, but it can actually be broken down into 3 fairly simple patterns that can be looked for. And so these are right here, and we'll go through these. So the first pattern is the 3-atom delocalization pattern. And so what that looks like is it's very common for 3 atoms to kind of share electrons in a way that delocalizes them a little bit. So as an example of that, if I look at this vinyl alcohol right here, what I can do is draw something like that. That leads me to a resonance form that looks like this right here, and I should be careful to add in my positive charge. And so what you're kind of looking at here is resonance explanation for the fact that this pair of electrons on oxygen is somewhat donated towards the carbon atom at the end here. Here's a slightly different example where instead of a neutral molecule to start, we're starting with a cation. And so delocalization of this cation can be observed, and it's shown through resonance like so, where again I'm trying to show that a pair of electrons, this time this pair of electrons in the pi bond, is delocalized not just between these 2 atoms, but also to the 3rd carbon right here. And so if I draw that resonance form, you should get to a structure like that one. Finally, I'm going to throw you a curveball here, but you can also draw resonance forms for unpaired electrons. So you can take a molecule like this one, where there is a single unpaired electron on this carbon. That does make this carbon neutral overall. And it turns out that this unpaired electron is delocalized across 3 atoms. And when we deal with unpaired electrons, we kind of divide up our electrons using kind of half-headed arrows. So crucial to see here that I've drawn only half of the head of the arrow here to show only 1 electron is taking part in this process. So I will draw it like that. So what I'm showing is that we're essentially breaking this pi bond into unpaired electrons. One of those will end up on the left carbon. The other one will then pair up with the black unpaired electron here. That gets us to this resonance form. So again, this pattern is very common. 3 atoms, all with some sort of a p orbital, spreading electron density across. The other common pattern is when you have multiple pi bonds that are so-called conjugated together. And so an example of that would be this molecule here. So I have a pattern of conjugation, which is a pi bond, sigma bond, pi bond, or double bond, single bond, double bond. And when that happens, those double bonds or those pi bonds are in conjugation with each other, and we can do resonance arrows that look like that, getting us to a final resonance form that looks like the one on the right here. And so what you kind of see is that now we're saying that these 4 pi electrons are delocalized over 4 total atoms, right? It's not 2 pi electrons on 2 atoms, 2 pi electrons on another separate 2 atoms, but rather all 4 across 4 atoms. Right? The consequence of doing that is you might end up seeing a little bit more negative charge on the oxygen and a little bit more positive charge on the carbon here. All right, a final pattern is just between two atoms, actually. And so what that looks like is when you have a pi bond between atoms of differing electronegativity, it's commonly the case that you can think of the pi bond as being delocalized like so, giving you a resonance form that looks like this one, where it puts a negative charge on oxygen and leaves a positive charge on carbon. And so we're thinking of it as delocalization, but in some way it's almost like it's localizing the charge more on oxygen at the consequence of making carbon more positively charged. So all of resonance will be built from these three patterns. We can kind of combine all these patterns together to get to different resonance forms. And when we're looking for different resonance forms, we want to be looking for resonance forms that are the most significant ones, because those are the ones that will contribute most to the weighted average. And of course, those that contribute the most to the weighted average should be the ones that explain the most of the molecule's properties. And so that might seem like a daunting task, but it turns out what we're really doing is actually the same thing as what we do when we're drawing Lewis structures. And so a more stable resonance form is going to be a more stable Lewis structure. And so in rough order of importance, what we'll want to do is to look for these types of features in our resonance forms. So the first thing we try to do is to just minimize the number of formal charges in our molecules. So an example of that would look like this right here, where I have this molecule acetone on the left and its resonance form on the right. And so even though the resonance form on the right is significant, I would tend to favor this one as being the more significant resonance form. Right? And I would recognize that this is a double bonded carbon-oxygen, but at the same time I would recognize that there is going to be in this molecule some amount of partial positive nature at that carbon, some amount of partial negative nature at the oxygen. So the second thing that we look for is to maximize filled octets in the structures. And so here's an example of that. I have this cation on the left and its resonance form on the right. So if you're looking at this, hopefully we're able to recognize that this carbon that's a cation here, or a carbocation, only has 6 electrons around it, so it does not have a filled octet, whereas on the right here, this resonance form does have a filled octet. And so what we would think is that in general, this is actually the better representation of the molecule. The third thing that we'll do is to try to stabilize negative charges, and we can do that a lot of different ways. The first is to just find resonance forms in which our negative charges are on the more electronegative atom, because the more electronegative atom will do a better job of stabilizing negative charge. And so that commonly will be the case with oxygen, so we will get used to seeing a lot of oxygens carrying negative charge. Another periodic trend that will follow is to put charges onto more polarizable atoms. So in this case, we're comparing sulfur to oxygen. Turns out the polarizability of sulfur adds a lot of stability, so this resonance form might be a little bit preferred even though oxygen is a little bit more electronegative. Finally, we will prefer certain hybridizations of atoms over others, and what we're looking for is how much S character there is in the hybrid atom. So we'll favor atoms that have more S character. So in an sp2 atom, you have 33% S character. In an sp3 atom, you'll have only 25% S character. And because S orbitals are thought of as being a little bit closer to the nucleus of the atom, we think of them as being a little bit more electronegative. And so if they're a little bit more electronegative in the S orbitals, then whichever hybrid orbitals are more S-like, those are going to be the ones that do a better job of stabilizing negative charge. And that's why we get this trend right here. Finally, we will want to stabilize positive charges in our resonance forms. And the first way to do that is to favor resonance forms that have positively charged carbons, or again, carbocations, that have more degrees of substitution around them. And in the future, we'll talk about why that is, but for now, we'll just believe that that's true. And so since that is the case, what we want to see here is that the left resonance form has a carbon with 3 other carbons around it. That should be the one that's a little more favored. We'll also want to avoid putting positive charges next to or nearby electronegative atoms. Because electronegative atoms are trying to pull in electron density, we don't want there to be a lack of electron density to pull it. And So for that reason, we would prefer resonance forms like that one right there. And then finally, kind of in the opposite of when we stabilize negative charge, if we're trying to stabilize positive charges, then we want to put the positive charge on an sp3 atom because it has less s orbital character. So finally, I want to walk through an example here of how this might work given a molecule. Like, what are we trying to take away from this information? So when I see a molecule like this one, my question in my mind is really, where does this molecule exhibit any amount of partial positive or partial negative charge? So given this molecule, I definitely especially recommend when we're starting out with resonance to fill in all lone pairs and make our life easier. And then to kind of look at, well, what could we do here and what kind of resonance patterns do we see? And so when I'm looking at this, I kind of see I have conjugated pi bonds here. I see I have a lone pair that's a single bond away from a double bond. And I have another lone pair here, a single bond away from a double bond. So those motifs are kind of the patterns that looked like this, right? Earlier we had seen a pattern that looked like this one. So I saw a lone pair that was a single bond away from a double bond. That allowed me to draw a resonance form like so. And I'm seeing that same pattern on the left here and on the right here. Right? And so if I start off, I'll just go toward the left. I can draw a resonance form like that. Fill in my formal charges. And so there you go. That's one valid resonance form. Duplicate my molecule here. And I can again fill in my lone pairs here. And my goal being that now I'm going to look for the resonance of this lone pair to the right. So delocalization of this lone pair toward the right side. I'm going to look for the delocalization of this lone pair toward the right side. And I can kind of do the same thing. Right? I can go like so. I can turn the lone pair into a pi bond, this pi bond into a lone pair. That should get me a resonance form that looks like this. And finally, we can look at that conjugated pi bond situation. So I'm going to look at this again. And so what I'm going to do here now is to combine some of those patterns together. So if you recall, the conjugated pi bond pattern was to go and do something that looks like this. And so I'm going to do the same thing here, but kind of start a little bit further away. So I'm going to start from the lone pair on the nitrogen. I can then go from the pi bond, instead of going to a lone pair here, so that's what I did on the left here. Instead of going there, I'm going to keep going. And then at the end, I'm going to essentially treat these last 3 carbons as another 3-atom delocalization situation, and thus end with a pair of electrons on the last carbon atom here. And so this is definitely at first a little bit challenging to do and see, but after getting used to it, resonance will turn out to be a very simple and powerful tool for us to be able to answer this question, right? Where does the molecule exhibit partial positive, partial negative charge? Well, my 3 resonance forms tell me that the oxygen will have some amount of partial negative charge because of this resonance form. The carbon right here will have some amount of partial negative charge, and the carbon at the end here will have some amount of partial negative charge. Additionally, all this drawing will tell me that the nitrogen will definitely have partial positive charge, right? And we should expect that there's a lot of partial positive charge on nitrogen, and then a little bit less each on the oxygen and these 2 carbons. Finally, we should expect that the resonance form up here is probably the most significant one because it has a negative charge on oxygen compared to all these negative charges on carbon. So that was the valence bond theory approach for explaining delocalization, and it did so by using the concept of resonance. Now let's quickly look at the Huckel theory or molecular orbital theory approach to dealing with delocalization of pi bonds. So the idea is pretty simple. We are basically taking just the pi bonds, so ignoring the sigma bonds. We're only thinking about pi bonds, and we're going to perform linear combination of atomic orbitals of the atomic orbitals responsible for those pi bonds. And so the steps are fairly simple as well. So we want to count up how many atoms are involved in the pi system, and then we will just mix all of their p orbitals that are involved in the pi system together to create exactly that many pi molecular orbitals. Because if you're doing molecular orbital theory and you mix n number of atomic orbitals, you should get n number of molecular orbitals out. Finally, when we do this, we want to do so in a way that kind of gets us to molecular orbitals of increasing energy. So the principle is to put combinations that are more kind of in line with each other as being the lowest in energy, and the more kind of flips of signs of p orbitals there are, the higher in energy that molecular orbital will be. Another rule that we won't explain the why of is that we want to make sure that the symmetry of the molecular orbital matches the symmetry of the molecule. And I think it'll help once you actually see the example. So we'll look at this molecule here, butadiene. And butadiene has 2 pi bonds, here and here. And those 2 pi bonds are separated by a single bond, so that's kind of our trigger to think of delocalization. And if we look at this, there are 4 atoms that are shared across those 2 pi bonds. So that means that we're going to have 4 carbon 2p atomic orbitals mixing together. That's going to mix to create 4 pi molecular orbitals, and I'm going to call those pi 1, 2, 3, and 4, respectively. And so here's the part where you get to kind of see all of these flippings. And so the idea is that I'm drawing in a p orbital on each of these carbon atoms, and I'm trying to mix and match my phasings. So again, the lowest energy way to do all of this, with our energy axis looking like this, is to make sure that all of the orbitals are facing kind of the same direction. So they have their phasings the same way. So that means I would fill it in like so, because that kind of maximizes the amount of interaction that is constructive between the different atomic orbitals. And so what that means is that I would view this as having only the planar node kind of going across the molecule here, and really people just ignore that and say that this has 0 nodes between the p orbitals. The next molecular orbital up should have 1 node between those, and if I want to keep the kind of left-right symmetry of the molecule, then I do it like this. And then pi 3 should then thus have 2 nodes, and to do so while keeping a left-right symmetry would look like that. And then finally, the highest pi molecular orbital will have all opposite phasings in the p orbitals that we're mixing. So that's what the pi MOs look like, but of course we have to add our electrons in. And going back to the structure of butadiene, it looks like we have 2 pi bonds, and each of those pi bonds is 2 electrons. So in total we have 4 electrons to put in, right? And so if I fill those in from bottom up, that means I fill my molecular orbitals like this. This means that for butadiene, we filled the first 2 molecular orbitals and the next 2 are empty. It turns out very conveniently that the overall situation for these 2 molecular orbitals is bonding in nature, because there's more constructive overlapping of orbitals rather than kind of this lesser amount of destructive overlap. Whereas the 2 higher energy pi molecular orbitals, pi 3 and pi 4, are actually anti-bonding orbitals because there are more destructive interactions between atomic orbitals. I think it might help to look at what these pi molecular orbitals actually look like relative to my atomic orbitals that I've drawn in. So I'll turn these on here. And so what we're looking at right now is, this is butadiene. You can kind of see the double bond here, single bond, double bond that's drawn in. If I turn on the side, you can kind of see how the p orbital from this carbon is overlapped with the p orbital of that carbon, p orbital of that carbon, p orbital of this carbon, and they're all the same phase, so they all mix across and kind of merge together, right? So this is the pi 1 molecular orbital. If I go to pi 2 now, if you look at the atomic orbital drawing I did here, you can kind of see that there's a pair that are lined up right there, and then a pair of atomic orbitals lined up here. And that's exactly what you see in the MO, kind of this pair of bonds here. And the nice thing that you see here is that it kind of shows how our line angle drawing sort of matches some aspect of reality, right? It sort of gives us these two separate pi bonds. What the line angle drawing doesn't capture is this molecular orbital where there's also interactions across these two carbons, and that's delocalization. Finally, I just want to show you the pi 3, which is unoccupied, so it's in a different color scheme here. But again, you can kind of see where those p orbitals are coming from. And here's the pi 4. It's interesting to go and compare the energies of these molecular orbitals with that of a molecule where there is no conjugation between pi bonds, or there's no extra delocalization. And so the simple example of that would be the molecule ethylene, which is just kind of our two carbons double bonded together. And so if you do that, I'm going to pull this all the way over here. What you see is that the two pi molecular orbitals of ethylene, the lower one, pi 1, is a little bit lower than the pi 2 of butadiene, and the upper one for ethylene is a little bit higher in energy than pi 3. Let me pull that out to the right here. And so if you fill in the electrons for ethylene, there's only 2, so it looks like this. There are some interesting observations that we can make. So overall, it is true that for 4 electrons, it would be better to put those 4 electrons into butadiene's orbitals. That's more stable than it would be to take 4 electrons and put them into 2 of ethylene molecular orbitals. So again, that means that butadiene overall stabilizes those pi electrons more than 2 molecules of ethylene do for 4 pi electrons. That's weird because there is this counterintuitive idea here that a pair of the electrons in butadiene, 2 of them, are actually higher in energy than any of the electrons in ethylene. And so this is a common pattern that shows up in chemistry, which is that in order for butadiene to kind of overall be more stable, it's sacrificed the energy of the pi 2 molecular orbital to gain a lot more energy in the pi 1 molecular orbital. So in many ways, butadiene is more stable, but it also has a pair of electrons that are less stable. Okay, so that was a look at how we explain delocalization of pi bonds across a molecule in conjugated systems using both kind of a valence bond theory approach that's been modified by the concept of resonance, and then a molecular orbital theory approach that's been modified by using Huckel theory to make it simpler.